It's a lazy, warm evening. Lenny and George are lying in the grass looking up at the sky. Tell me about the stars, George. Are they particles? Kind of, Lenny. How come they don't move? They do, Lenny. It's just that they're very far away. There's an awful lot of them, George. Do you think that guy Laplace could really figure them all out? Well, that's just the introduction to this chapter in the book. So that kind of sets uh, the introduction tone for like what the chapter is about. Basically, how did Laplace figure all of the stars, all of the motion and the kinetics of all the stars in the sky? Well, it's the system of particles, and as we saw in previous videos, this is a particle can be just about any point, an arbitrary point. It could be a rock, it could be a person, it could be planet Earth in the system of the solar system, the planetary system. So, and when we discuss about the system of particles, well, we discuss about the forces acting upon them. There are many types of forces, such as friction, force by the wind, force on the forces, the electrical forces, the gravitational forces, all of them. But of all of them, uh, charges and masses are considered to be intrinsic properties of a particle, and specifying them is part of specifying the system itself. So, to talk about charges and masses are considered to be intrinsic properties of a, a, a particle. Specifying them is part of specifying the system itself. Apart from the intrinsic properties, the forces depend on the location of the particles. For example, the distance between an object determines the electric and gravitational forces that one particle exerts on another. Suppose that the locations of all particles are described by, let's say, x, y, z for the first particle, and x2, y2, z2 for the second particle, and so on. Then the force on any one particle is a function of its location as well as the location of all the others. So it means that the force on one particle and any one particle, I, this is a vector, so we put the bar on top of it, is equal to, it's a function of its location as well as the location of all the others. Which means that to write it like this. So basically it means that force on ith particle is a function of positions of all the particles. The symbol R bar in the floor brackets stands for collective location of every particle in system. Another way of saying this is that the symbol represents the set of all position vectors. Now once we know the force on any particle, let's say particle 1, we can write the Newton's laws of equation of motion for that particle. So if you were to write the Newton's laws of motion for particle 1, given you know its position, you would write it like this. M1 mass of that particle solution. Now it can be also written as m1 t square 1 divided by t square. Now You could write it for every single particle. You could just replace this one by I, and that uh, implies that it is for all these particles. Now, you can write it in component form. So x of I, you know, x plus mi t square xi by t square. We will call this as question 1. So likewise, can wait for like y and z. So similarly, y and z. Here, x plus z are the components of force on that particle, and the symbols, the flower bracket x, y, and z represent the sets of all x coordinates, all y coordinates, and all z coordinates of those particles. So whenever you see this, it means in that particular coordinate system. Now, so how many equations are there in all? Well, this set of equations makes it clear that there's an equation for each coordinate of every particle, which would tell Laplace's vast intellect how every particle moves if the initial conditions were known. So, so now we kind of think like, well, there are total of 3, isn't it? So for n particles, we have 3n equations to determine everything about them. What about the space of states of a system of particles? Let's talk about space of states. The formal meaning of the state of a system is everything you need to know with perfect accuracy to predict its future given the dynamical law. The system describes everything you need to know to predict with perfect accuracy its future given the dynamical law. So the space of states, also called it the state space, is a collection of all possible states of the system. As we can recall from the lecture 1, the state space was typically a discrete collection of possibilities for let's say heads or tails. It would be H and T. Those are the only two possibilities, and only one state would be the active state for at a given point in time, and so on and so forth. Now, Newton's law tells you that acceleration is what determines the velocity of the particle, and which means that in order to determine which means, so basically the state of a system of particles consists of more than just their current locations. It also includes the current velocities and the rate of change of velocities. Uh, this is why we say that like if you have studied the quantum physics, if you studied like any physics, I mean not any physics, the quantum physics mainly, you may recall that uh, the Heisenberg's uncertainty principle. You cannot fully determine the position and momentum of a particle. The momentum is basically mass times velocity. So remember that the position and velocity are the two key things, and we take position and momentum instead of just position and velocity. Although momentum is just mass times velocity, so this momentum, even though it can be something that can be derived from velocity, if we take momentum and position as the two key things that define the system, the state of a particle. So now we are saying that we need not just 3n equations, well, that would be 6n equations. 3 for positions and 3n for positions and plus 3n for the velocity. So we need 6n equations for n particles. So consider the space of states of system of n particles. So now we know we need 6 and so to specify the state of system we need to specify the state of every particle. This obviously means that the space of the states is 6n dimensional. 3 position components and 3 velocity components for each of the n particles. One may even say that the motion of the system is a trajectory through a 6n dimensional space. Now this is, we're talking about mathematical dimensions here. This is not actual spatial dimensions. So the state space is 6n dimensional. Why is it that 3n components in equation 1 are enough to determine how the system evolves? So we saw in equation 1. Well, are we missing half the equations? Because they clearly don't contain velocity, do they? Let's go back to a system of single particle with the specified forces and write Newton's equations using the fact that acceleration is the rate of change of velocity. There's no expression for the velocity in the, so let's just say dmv t plus f. There's no rate of change of, well, this is the rate of change of velocity, but there's no expression for velocity here. So this is, remember too that this is just rewriting of the equation 1. So let's add another equation explains the fact that velocity is the rate of change of position, which we know already. So which means that m dv by dt equals fi and dri by dt vi. Well, this should be our new set of equations. And next topic, let's go to the momentum. Again, this book is just about concrete topics. It doesn't flesh out everything because I mean, this is not. If you're studying like physics as your life subject, then life or like studying physics for your entire career, then this book only covers the important stuff and not everything. Obviously, this book is something that's the most important. So for even though this is physics is not one of my daily life subjects, I am going through this just because it's physics. It's important. Elon Musk says. I mean, not just Elon Musk. Many would agree with that. Even like Andre Karpathy, they would all agree physics is something that is very important. And also Temis Hassabis. Now, momentum and phase space. If you're struck by a moving object, the result depends not only on the velocity of the object but also on its mass. So obviously, a ping pong ball at 30 miles per hour is different from a car carrying at 30 miles per hour. So momentum is defined as p small p m v m type v. Now, since velocity and momentum are closely linked, we can cause momentum and position instead of we can use momentum and position instead of velocity and position. And when the state space is described this way, it's called the phase space. So remember to this is called as a phase space, like just a state space. They're kind of confusing, like, but state space just has position. Like it has only mm, R and V. this one has position and momentum. So no, this is not called as configuration space because that term is used for something else. So we namely three-dimensional space of positions, and which is just the positions. So we call this as phase space. So in a way, we can say that like configuration space, configuration space plus momentum space equals phase space. This has only R, this has P, which has both of them. Not that different. So, so I wonder why we go the trouble of replacing the intuitive concept of velocity with more abstract concept of momentum. And as I said before, it's hell of a yes for me. And let's go to the next topic, that is action, reaction, okay, reaction, and conservation of momentum. Now, for every action, there's an equal and opposite reaction, as we saw in the older chapter. So, written as oh, by the way, so just to revisit the idea of momentum, let's call it position like this. Let's call it 3. And yeah, so action and reactions, we can write it like this. So force on particle I due to particle J, and total force acting on particle I is sum of all forces on particle I from different all other particles J. And remember too that since we talk about action and reaction, they are opposite to each other. So action, the force on J from I would be exactly opposite in direction, but equal to equivalent in the amount. And that's the equation. So now since the momentum is conserved, the rate of change of momentum of any particle is the sum of forces due to all other particles, which means that you can write uh, so now we're talking about the momentum conservation loss of momentum. So if you write pi, again this is rate of change of momentum as a sum of all forces on it. Rate of change of momentum is basically force. It is a force quantity. And if we were to add up all the forces, rate of change of momentum, which means iterating over all the combinations I and j, well that just cancel each other. So it means that write like this: sum of I, p, I, j, just I, well, that is equal to 0. The law of action and reaction, so they will cancel all of them. This comes from the fact that this comes from this fact. So do that, then we get this. So let's consider a 6n dimensional space of position and momentum. At every point, the intercollection of momenta are specified. So it follows that every point in this phase space is partially characterized by the value of the total momentum. You could go through phase space, labeling each point with its total momentum. Now imagine starting the system of particles at some point. As the time evolves, this phase point sweeps out path in the phase space. Now I could describe the partial derivatives in a separate session. So it's quite useful topic for this chapter and pretty much anything that has to do with AI or anywhere partial derivatives are useful. So and yeah, this is the equation of law of conservation of momentum that completes this chapter.